My name is Claudia de Torre, and I am a PhD student with the Wellcome and EPSRC Centre for Surgical and Interventional Science at University College London. And for IPCAI 2021, I will be presenting our work on autonomous pick and place using the dVRK. Allow me to start with a brief overview of this presentation. First, I'm going to describe what is the motivation behind this work, followed by the aim of the research. To move on, the description of the framework and system configuration. We follow the main section of the methods characterized by the system calibration, rail detection and kidney registration, to end with dynamic time warping trajectory planning and control feature. I will then introduce the preclinical user study, followed by the description of results, and ending with some discussion. This work is framed into the context of intraoperative ultrasound scanning for minimal invasive surgery. On the left, we can see a video sample from the current state of art of the procedure, where on the top, we have the surface that will be scanned, the ultrasound probe held by the surgeon, and the second robotic tool. The ultrasound output view is normally displayed below the endoscopic one. When the procedure starts, the surgeon swipes the probe over the target surface, checking the output of the ultrasound images on the bottom, to then mentally maps the location of the tumor over the endoscope image and uses this information to outline the tumor margin with the electrocauter tool, as we are seeing right now. On the right, we have the proposed novel approach, which relies on the use of a pneumatic flexible attachable rail, which is attached on top of the kidney and used as a guidance of the ultrasound scanning. This video briefly shows how the PAF rail is meant to be used during intraoperative procedure. We can see that the probe is engaged with the rail, was sitting over the kidney phantom, and slide along its length. The aim of this work is to develop a software architecture that allows to autonomously execute the pick and place task, triggering the start of the scanning procedure executed by the surgeon. Specifically, the paper contributions are a trajectory generation using dynamic time warping, a control scheme based on visual servoing, a comparison between two different surface registration techniques, and a preclinical user study comparing the performances of 5 surgeons. I'm going to give a brief description of the framework using this work now. The workspace is characterized by a porcine kidney, the PAF rail, the robotic tools, and the stereo endoscope. The software architecture relies on a calibration node, a detection one, and one from planning and control. I'm now going to give more details about each part of the software architecture, starting from the system calibration. A checkable pattern was used to perform robot calibration. 45 frames were acquired from different endoscopic poses and used as input of the MATLAB toolbox for stereo calibration and obtain the camera parameters. 7 more frames were used to determine the pose of the endoscope compared to the checkerboard. In order to assess the accuracy of the calibration for the 2 robotics tools considered, respectively the large needle driver and the probe grasp, we perform a probing procedure, as you can see from the animation, acquiring the coordinate of the checkable corner through the dVRK embedded software and compare those values with the one extracted from the endoscope. To quantify this measure, we use the fiducial localization error, which computes the error between coordinates of the 2 different point clouds. The results obtained show that the large needle driver presents higher accuracy. Therefore, we selected this instrument to execute the autonomous task. Regarding the rail detection and kidney registration, the rail is equipped with a small checkable pattern, which was used for tracking it using the MATLAB triangulation function. Knowing the geometrical model of the rail is then possible to compute the position of the grasping site. For kidney registration, 2 different procedures were compared. The first one relies on the detection of the ink marker using the stereo endoscope. The second one uses the large needle driver to probe the marker position and reconstruct them using the robot kinematics. Comparing the results with the ground truth, represented by the distance between the markers of 50 mm, we can notice that the probing technique appears to perform better. In the last section of the methods, I'm going to describe the dynamic time warping trajectory planning and control feature. In order to generate the desired trajectory, two main algorithms parts were involved. First, the entire pick and place task was divided into different steps. Specifically, in step 1, the tooltip starts from the on position that is represented by the following Cartesian coordinate. In step 2, the rail reaches the grasping site, compute with the rail detection algorithm. In step 3, the tool drives the rail back to the on position, to end with step 4, where the robot tool approaches the kidney surface to properly locate the rail. As part of the control feature, step 4 is also characterized by an additional check, which compares the position of the rail obtained with the kinematics of the Da Vinci and the one obtained with the kidney registration to check if the placing of the rail has been executed correctly. Dynamic time warping has been used instead to estimate the path followed between the steps previously described. Specifically, we recorded 10 different executions of the task by a train operator, acquiring both Cartesian position and the joint value of the robotic arm. We then take two of these trajectories at a time and minimize the distance between them using the following dynamic time warping formulation, where specifically Wi are the element of the distance matrix and P is the dimension of each trajectory. Each element of the matrix is computed as follows, where capital TJ and capital TK are the selected pair from the trajectory, and D represented the values coming from the previous computation. Combining together these two pipelines, we were able to completely generate the final trajectory. I'm now going to describe the preclinical use study that we perform in this work. 5 surgeons were involved in the acquisition with different years of experience and no previous knowledge of the path rail system. We asked them to perform 3 different tasks. The location one, where they had to pick the rail from a starting position and locate it over the kidney. The sliding, in which they had to engage the probe with the rail and slide it along back and forth. And the last one, which is the kidney motion task, where they had to perform circular movements to reposition the kidney, as shown in the picture. Approaching the end of this presentation, I'm going to describe the results obtained from the experiments. For the automation part, we executed the design task for a total of 40 times, reaching a success rate of 35 executions over 40. The Cartesian trajectories of the successful task are shown in the image. Regarding the failed executions, in 5 cases, the robot was not able to properly grasp the rail because the position reconstruction was not matching the actual rail position, as is possible to notice in the image, where the failed trajectory represents a bias error on the z-axis component. Additionally, in 4 of the successful execution, although the robot managed to correctly grasp the rail, the position is reconstructed wrongly, specifically farther away than the real one. This error generates a sliding of the tool against the surface plane, reflected on this horizontal pattern highlighted in the image. Moving forward to the user study results, here we can now see some samples of the video showing the first time the first surgeons executed the tasks. Each of the surgeons had to repeat each task 3 times. For each execution, we measured the following values and averaged them. To start with, the execution time, measured in minutes. The success rate, represented by the ratio between successful execution over the total number of attempts needed. The difficulty, scoring between 1 and 10, and the willing of use, always between 1 and 10, describing how much they would begin to use the device in real clinical practice. To sum up the work contribution, we presented preliminary experiment showing the automatic positioning of the path rail is possible by combining motion planning and visual servoing. We implemented and compared the calibration accuracy with 2 different robotic tools using the dVRK. We ran a preclinical study using 5 surgeons using for the first time the PUF rail. The main outcomes of this work can be summarized as that the average execution time of the automated task was 42 seconds. The average execution time of the location task executed by the surgeon was instead about 1 minute. Results from the preclinical study highlighted the need to build an inherent user flexibility and make the system compatible with every tool. Regarding the main limitation and future work, there is definitely the need of a more robust vision algorithm, considering, for example, tissue deformation. Also, the need to analyze the effect of bleeding and or partial occlusion on a visual surveying algorithm. Further work is also needed for adaptive control in the presence of physiological motion, and more comprehensive clinical workflow studies are also necessary, including the use of a functional ultrasound probe. Thank you very much for your attention. I'm going to attend the interactive session, so please feel free to save your question for it or don't hesitate to send me an email and I will happily respond. Thank you.